Hello, my name is Sam Albert. I want to begin by acknowledging my co-author and advisor, Dr. Hans-Peter Schaub. And today I'm presenting our work, Co-Delivery of Multiple Small Probes to the Martian Surface. So my motivation for this work really began earlier this year. I was fortunate enough to participate in a workshop hosted by the Keck Institute that focused on near-term concepts for lower-cost exploration missions to the Martian surface. In particular, something that we discussed a lot were regional network missions of small rough landers. In particular, maybe there's a regional seismic network located in an area of known seismicity, like, for example, Cerberus Fossae, shown here in this figure with results from the Mars InSight lander. And one example that could be used for that small rough lander is the SHIELD concept under development at JPL. SHIELD relies on having a very low mass to drag area ratio, and it is a passive uncontrolled entry vehicle. It has no parachutes, no retro propulsion, and it relies on crushable material to attenuate the final impact, and instruments are then designed to survive something like 1,000 Earth Gs on landing. So this all had me thinking about what design trade-offs exist for missions that would deliver a regional network of small passive probes to the Martian surface. So to start with some assumptions on this problem, we assume that all of the probes are small passive ballistic rough landers and that there are at least 4 in the network. All of the landing sites are between 10 and 200 kilometers apart, and they should be spread out in more than one direction. In other words, not just strung out in a line. That's probably not very good for observability. We assume that precision landing is not a requirement for any individual probe, and that we care more about the general size and shape of the network. The probes approach Mars from a single carrier spacecraft that is on an entry trajectory, and then separate mechanically from that carrier spacecraft in balanced pairs across the center of gravity. Finally, we assume that these jettison events occur somewhere between 5 and 0.25 days before atmospheric entry. So to get a sense of this problem, we started by jettisoning 4 probes all at the same time, one pair in the plus or minus along track direction, and the other pair in the plus or minus cross track direction. And this is a scenario with an entry azimuth of 80 degrees, so nearly due east. And as a result, the circles representing the along track jettison are spread out mostly in longitude, and the squares representing the cross track jettison pair are spread out mostly in latitude. A key takeaway of this figure, in which we are holding jettison time constant at 1 day prior to entry, and we're varying the speed of jettison from 5 to 40 centimeters per second. And one key takeaway here is that those along track jettisons achieve a lot of spread on the surface in the downrange direction, whereas the cross track jettisons achieve much less separation on the surface in the cross range direction. And there are similar takeaways from this figure. In this case, we are holding jettison speed constant at 10 centimeters per second and varying the time of jettison from 3 to 0.25 days before entry. For each of those scenarios, we also compute the great circle distance between all of the pairs of probes on the surface, and then take the minimum and maximum of those values. And those are shown in this table here for all of the different combinations of jettison speed and jettison time. What I find most interesting about this data is that it behaves quite linearly. This isn't really a surprise because we're essentially applying small perturbations to some reference trajectory. So this is just local linearization. But I still find it interesting that this works despite the nonlinearity of the dynamics at play. Here I'm plotting max distance versus jettison speed, but this also works versus jettison time, and it also works for the minimum distance parameter. So this linear relationship, approximately linear relationship, allows us to apply a basic linearized targeting scheme. This is very similar to B-plane targeting, but instead of targeting the B-plane, we'll be targeting all the way down to the surface for small changes in latitude and longitude. And so we will linearly approximate that sensitivity using this Jacobian matrix, which we will compute numerically using finite differencing. It's non-square, so when we invert it, we'll use the least norm solution. And what we end up with is we can compute the jettison velocity that will achieve some change in latitude and longitude of the landing site while minimizing the jettison speed, the magnitude of this jettison velocity vector. So we apply that targeting scheme here, we're targeting landing sites that are spread out in a circle around the central point, a circle with radius of 1/2 degree. And we're showing two different scenarios here, one with a due east entry azimuth and the other with a due north entry azimuth. And there's more details in the paper. This figure essentially shows that the targeting works pretty well. And then the figure on the right, we are showing the jettison speed versus angle between the offset direction on the surface and the downrange direction. And this reinforces a conclusion that we drew from the earlier plots, which is that these separations in the downrange direction at the angles 0 and 180 require much less jettison speed than the cases that are asking for separation in the cross-range direction, these angles of 90 and 270 degrees, they require a much higher jettison speed. So to say it more simply, it's a lot easier to achieve downrange separation on the surface than it is to achieve cross-range for this scenario. And we also wanted to test the bounds of the region in which this linearization is appropriate in the first place. So this is all for one jettison 1 day before entry, and for this particular scenario. And we're computing the error between the targeted landing site and the actual landing site while varying the size of that desired offset on the surface. So for anything below 1 degree, the errors stay below 10 kilometers. They're below 5 kilometers for downrange separation. They start getting worse. They begin to reach about 100 kilometers of error by 3 degrees desired separation for cross range, with downrange error following closely behind. And then it blows up. And by 6.5 to 7 degrees of desired separation, you will actually miss the planet if you apply this targeting scheme. So that's just to give a sense of how far out you can get before this stops being applicable. We then design an example network, and so we're placing this in Cerberus fossae. We have in this case 3 pairs of probes for 6 total. And because we assumed that these jettison events occur mechanically, we don't necessarily want to just totally minimize the magnitude of jettison speed. It might be more beneficial to match the jettison speed between each of these events, such that, for example, you might be able to use a common spring system for each of the jettisons. So to figure that out, we just plot, we do this linearized targeting at a number of different jettison times and compute the magnitude of jettison speed required for each of those. We do this for each of the unique probe locations, and then we just pick a desired jettison speed that's relatively low while still intersecting all 3 curves, and we use a root solver to precisely locate each of these intersections. So having designed this nominal network, we apply relevant uncertainties and do a Monte Carlo analysis, in this case with 5,000 trials. We are dispersing atmospheric density, entry flight path angle, and entry velocity. And all of those apply equally to all of the probes. The carrier spacecraft state is dispersed at entry and then back propagated to each of the jettison times. And then we're also dispersing at plus or minus 10% error on the jettison speed for each of the probes, as well as some error in the probe ballistic coefficients, and those are dispersed independently for each of the probes. So these results, the blue dots are the landing sites for each of the probes in the Monte Carlo analysis, and we can see they vary quite a bit, especially in the downrange direction. That's absolutely expected, considering they're not applying any control at any point actually after jettison. But what's interesting is that we can quantify the distortion of the shape of the network, and there are quantitative results in the paper. Here we're just going to look at these red pentagons, which show the worst case scenario for that shape error, the most distorted that the network gets. And it actually looks still pretty similar to the nominal shape. It's stretched a little bit in the downrange direction, but it still is well within the requirements of being a distance of between 10 and 200 kilometers between every pair of probes. So that's a key takeaway here, is that we can still target this network pretty well, even though there's a lot of variation in the individual probe landing locations. So with that, I just want to close by thanking NSTRF, thanking the Keck Institute and all the fellow workshop participants, as well as Mark Panning, Dan Burkhart, and Bobby Braun for their inputs to this work. I look forward to the in-person session. I'll take any questions then. And of course, if you have any from watching this video, please feel free to email me at the address listed here. Thanks.